And before starting, I would like to ask you a favor. Today I have a problem. We have a meeting, faculty meeting for the the pool of the new rector of Sapienza, and so we have a faculty meeting to be organized. And I would like to ask you only for this lecture to skip the intermediate break of 15 minutes and have a unique time from now up to 3:30. Okay, I'm sorry, but this is just a very special day today, and I want also to anticipate a point. We, as you know, we skipped the first week of lesson because of the delay in the opening of the lecture in the faculty, and I have in mind to recover these three lecture together during I don't know, morning or afternoon, better morning, because in the afternoon you typically have other lessons. And I will propose to you 2-3 proposals, and I will publish just a form or with options, and you can indicate your option, and I will and so we will decide together this lesson. Okay, 3 lessons, just a week, so 1 lesson recovering for a week, and so we will cover this gap in a few weeks, no problem. Okay, today I would like to conclude this refresh on social dynamics, and so after this refreshment, we will face the part of the course concerning the unsteady aerodynamic for a compressible flow. And after this block, we will have a block joined together these 2 parts for a unique coupling model for the elasticity. Okay, so we can start the recording, and then we can share this table here. Okay, so the scope was to study this problem, and yesterday, probably with some practical issues and problem on the device available, I prefer my tablet with respect to the fantastic clipboard at the moment. However, I don't know for the future, but at the moment I will keep to use this device here. However, this is the problem, and yesterday we opened a parenthesis in bracket. You introduce the eigenproblem associated to the mass and stiffness matrix. The eigenproblem associated to mass stiffness matrix is the following. Okay, and this is so-called 2 matrix eigenproblem and eigenvector, of course. So yesterday you discovered that you can find for this eigenproblem a set of parameters like lambda n for n equal to 1 up to the famous number we used yesterday, like 13, 7, I don't remember the detail, but something like that. Just to say, this number is the dimension of the mass and stiffness matrix. It's nothing to do with 3 dimension on 2 dimension. No, The dimension, this is the dimension of the discretization. So no physical meaning. So we are able to find a set of this constant and a set of these eigenvectors. Okay. Yesterday, Saltari tried to convince to you that this constant are real number positive, and therefore you can call this constant as the square of a number, and these eigenvectors are orthogonal and these two consequences are consequence of the fact that the mass metric is symmetric, the stiffness matrix is symmetric, and both are positive. This property implied this, and since these eigenvectors are orthogonal, you may introduce this matrix as the eigenvector matrix, up to 13, 7 to 8 eigenvector. So at the beginning, please suppose to extract the maximum number of eigenvector and eigenvalues, and the maximum number is equal to the dimension of the space in general. Okay, so you have 13,000 blah 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 eigenvalues, so omega square quantity, and 13,000 blah 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 eigenvector. This eigenvector can be organized in a matrix of all real quantity, and in particular lambda, real positive quantity. Indeed, I can imagine this lambda as a square of a real number, like omega. Okay, all this is algebra. Is algebra, not physics, associated to the matrix. The only physics associated to this algebra is the positivity of the matrix and the symmetry of the mass and stiffness matrix, because this positiveness is associated to the existence of kinetic energy, elastic energy, as positive quantity. As a function, positive quantity as function of the state space variable. The state space variable in origin are the strain. The strain is the state space variable in the thermodynamic point of view. But after discretization, the state space variable is Q quantity. Okay? So, this matrix is a matrix of eigenvectors in column, and the property of this matrix is the following. If you pre-multiply the stiffness matrix by zeta transpose matrix and multiply by zeta, you obtain positive number like K kappa in a diagonal matrix form. And when you pre-multiply this by the mass matrix, you obtain, this is a recap, yesterday recap, equal to positive quantity like mm. These quantities are positive because of the positiveness of this quantity is positive, this quantity is positive, and this positiveness is arising by the positiveness of the mass matrix and the stiffness matrix. And the story is that these matrices are related with the energy, blah, blah, blah. Okay. So, in this sense, the matrix are the eigenvector matrix are orthogonal through or by means of this mass matrix and the stiffness matrix. In fact, strictly the orthogonality property of the matrix are the following. Strictly speaking, a matrix is orthogonal if and only if, this is if and only if in English, if and only if A transpose A is equal to the identity. And since this symbol is identical to this, you may conclude that in the case of orthogonal matrix, the transpose matrix are equal to the inverse of the matrix. And this is a standard. But we are not, in this case, different. Because in this case, we have the mass matrix at the center here, or the stiffness matrix at the center here. We don't have the identity matrix. No, not the identity. And for this reason, this kind of orthogonality is called an orthogonality with respect to the mass matrix and orthogonality with respect to stiffness matrix. Okay? Look, another point, another important point about this constant. What is the meaning of this positive constant? Constant. This constant, Kn positive, also equal to 0, Mn positive. These constants are related to the choice of the normalization of the eigenvector. These constants depend on the eigenvector arbitrary constant. Chosen. In the sense that you have that, for example, zeta number 2 transposed mass matrix zeta number 2 is giving to you M2, okay? But if you take 7 by zeta 2, it's okay, it's the same direction, eigenvector, but with another constant, and you can apply this here, again, multiplying by, this is transposed, 7 zeta 2, and you should obtain 49, the old M2. This is the new M constant with respect to the old one. So this stupid consideration is a consideration just to convince to you that the entity of M and Q is depending on the eigenvector scale. So it's arbitrary. But the ratio between M and K is not arbitrary. The ratio, which is able to cancel the constant chosen, the ratio is going to give to you the eigenvalues. In fact, but the ratio the ratio, I mean, Kn on Mn equal to, it's easy to show what it is, because you have that by definition K on zeta n is equal to lambda m by zeta n by definition, and therefore if you pre-multiply this by zeta, the vector zeta n transposed zeta n transposed, you have that this quantity is k, small k, m, and this quantity is m, n. Excuse me, I've written this with the sub-index, not the super-index. So, oh my God. Oh, interesting. Everything cancelled? Okay, thank you. So, firstly, k zeta n equal to lambda n m zeta n, and therefore you have zeta n transpose zeta n transpose. This is k n, this is m n, and therefore lambda n, which is equal to omega square n, is equal to k n by m n. So the ratio, the constant itself are depending on the vector amplitude, eigenvector amplitude, but the ratio between the constant is independent by the eigenvector scale, but is exactly the eigenvalue. Okay? Okay. Algebra, all algebra. Now, by this algebra, you want to solve the ordinary differential equation. So, and this is also known as an eigen approach for solving the ordinary differential equation. We use the related eigenvector and eigenvalues for solve a linear differential equation. This is standard theory. Calculus number 2, analisi 2. Hopefully, sperabilmente. Note that we want to stress the fact that we want to keep a second order in the equation. The natural trend for mathematicians and system people is to convert everything in the first order. This is reasonable. But we want to keep the second order in this system of ordinary differential equation because we want to be linked to the physics of our vibration world. Okay? And so we prefer to keep the second order division instead of the division of the first order differential equation, but we are double order, you know. If you transform a second order to a first order, you are doubling the number of equations. Okay? This is possible, but we don't want to do this. Voluntary. Okay, what about this? The strategy of this solution. The strategy of this solution is a change of coordinate. The change of coordinate is of coordinate. I want to give you this further information with respect to what you know. Change of coordinate means from q hat finite element or q without hat. Q without nothing with nothing is finite element default. Okay, so q hat finite element, q finite element. But the transformation from the initial q finite element equation to another Lagrangian coordinate like q bar is equivalent or is dual. This is, in my mind, this is yin and yang, dual. Is dual to a change of shape function. Remember, u physical displacement is supposed to be decomposed in a number of new variable like this, qn or q hat, but these new variables are associated to this shape function. The shape function and the new variable are identical, are member of the same team, okay? But psi are known quantity. I introduced psi. Q are the unknown, okay? So if we are now introducing a change of coordinate here, necessarily, as one say, read inside the line, necessarily we are introducing a change of shape function. Correspondingly, necessarily, if we are introducing this algebraically, like in particular Q is equal to zeta matrix on the new variable Q bar, this is the change of coordinate I am introducing. Correspondingly, this implies a change of shape function from psi to psi bar. To be summed from n to, this is interesting point, I write here 30,473, yes, I should, and I write, no problem. But, I don't know, probably this series could be faster or slower with respect to the other one to converge to an exact solution. This is the point. This is the point. Okay? So, the physical quantity is the same. The same physical quantity to be approximated in this way or in this way here. Typically, people is most confidential to understand a change of coordinate in this way with a matrix like this. And this change of coordinate means that I can develop this. This means that your initial finite element state space vector is supposed to be equal to first eigenvector by the first Q bar coordinate plus second eigenvector. I am developing this matrix by vector product. Second eigenvector Q bar 2 plus up to the last eigenvector, like the 13, 7, blah blah blah. Q bar 13, blah blah blah. So I am representing the solution in a new base, algebraic base, in the space now of 30,000 and so dimensions. Is the space of the discretization. And I want to represent my old vector Q as a function of new variable in this way. But this point of view of change of coordinate is identical to suppose to change this. And I hope that Saltari convinced yesterday you on this point, in the sense that how can I define this? What is this psi bar and new shape function? What is this? What is this? What is this new shape function that corresponds to the change of coordinate from Q to Q bar? The answer was the following. This shape function can be described like a combination of the old finite element function through the eigenvector component. So this M new shape function corresponds to the use of the M eigenvector with component N combined by the old M finite element shape function, if you prefer, without any symbol upward here. And here we have to sum this quantity on N, like Naples. From 1 to 15 and so on. Oh, what does it mean? I'm confused. What is this? What is this sidebar? Okay. Remember what is psi? Psi are a 10th function with value 1 in the node N and 0 in the other. So combine this function with the component of the eigenvector. And therefore, the component of the eigenvector. So imagine to have our friend cantilever beam, our dear friend cantilever beam. And imagine to have this discretization in the final element, and imagine to have as zeta 1 eigenvector. Remember that in the finite element state space world, the component are the actual displacement of the beam. So imagine to have a zeta 1 vector the following component: this number. These are numbers. Okay? So this vector is 1, 2, 3, 4, 5, 6. You have 0.1, 0.2, 0.4, 0.5, and so on. 0.9 and 1.2. 1, 2, 3, 6 number, this 6 number here. Okay, what happens when you combine all these number, this one eigenvector, the number, you have to combine the number 1 component with psi 1 function plus the number 2 component of the same eigenvector with psi 2 function, and so on. If you remember the story, I announced it to you the day before yesterday. Here, look, if you have this displacement, through the psi function, you are able to approximate your continuous function, in this case, with a linear piecewise function. Why linear piecewise? Because the elementary 10th functions are linear. Okay? So, through the shape function, you can define a continuous function by starting by the vector zeta 1. So the vector zeta 1 is an algebraic quantity you can evaluate. The vector zeta 1 is this algebraic quantity, and by this algebraic quantity you can build here a continuous function psi bar 1, which is the reconstruction of this shape. No, I don't like this color. The reconstruction of this shape through the 10th on finite element shape function. Okay? So, this black curve is this, psi 1. psi1 is something recovered by the discretized final element word into the continuous word of the physics. Whenever you truncate the number of the element, you are currently approximating this quantity psi bar, but you have psi bar. So psi bar is something like an extrapolation of the eigenvector on the physical space of the problem. Okay? As the continuous solution is an extrapolation of the discretized solution into continuous word of our problem, in the continuous space word of our problem. Okay? I want to underline to you this interesting conclusion I have for you. Look, we have the physical vector at the end, we have that the physical vector is represented or expanded by a summation of psi without nothing, finite element shape function on the finite element coordinate. Okay? And this is an n summation on number of finite element. Number of finite element degree of freedom. Finite element DOF. But you can introduce this change of coordinate. In the yellow vision, this is one vision, and this is another vision. We have the yellow vision, and we have, oh, excuse me. Okay, we have the yellow vision, and we have the blue vision of the shape function. Maledetto. No. Okay. Now, look, if we consider this change of coordinate now, this change of coordinate, here, we have that Q is equal to zeta on the new coordinate. In component, you have that Qn is equal to zeta n m q bar m, summation in m. I have simply translated this change of coordinate in component. So if you apply this, you have the following, you have the summation psi n x q, and instead of qn we write summation. Let me write this summation in the safe side here. So this is an n summation, the original one, and this is the m summation, the other one. Theoretical to the same limit, number of degree of freedom and number of degree of freedom, the famous 30,000 and so on. So here you write Qn, and therefore you have zeta m n on Q n. So here you can clearly see what are psi bar functions. This is what are psi bar function. Oops, excuse me. So this here, this is psi bar function m, the definition. Exactly this definition here. And so at the end, here you have summation in M of your psi bar function on Q bar M, representing the same physical quantity. Okay? So the vision of the coordinate is very simple to have in mind. The mathematical vision of this yin and yang here is exactly this vision here. Let me complete my yin and yang. This is the blue one, and this is psi, and this is the yellow one. Where is it? Excuse me, I can see the pixel. Okay, okay, and this is the yellow one. This is Q and okay. Oh, in this sense, the change of coordinate to modal coordinate is a change of coordinate in terms of algebraic matrix, changing the new Lagrangian coordinate into the old one, and or a change of shape function from the old shape function, the psi hat, to the new one, psi bar. The coefficients relating this change of coordinate are the same, but pay attention, this coefficient, not this coefficient, which are the coefficient of the eigenvector matrix, in the case of Lagrangian coordinate, you have that the old are equal to zeta, the new one. But in the case of the psi function, you have that the new one and are equal to the old one combined. This is M, excuse me, and this is N. The new one are equal to the old one combined with zeta and M. The vision of the change of coordinate here is represented by a matrix notation in a compact form, but I can't represent down the change of shape function in a compact form because these shape functions are physical vector representing the displacement. Okay, the displacement field. These underlying psi are three-dimensional vector. In fact, three-dimensional vector are representing our physical vector U, the displacement. Okay. Okay, so this is the interesting vision of the new perspective coordinate. I have the possibility to change the coordinate, and I can do this in a double vision. Changing Q or changing psi is the same. Okay, this is the method. Well, now I can move toward a solution, and the solution is the following. Solution for M Q dot plus K Q equal to E. Aeroelasticity. In aeroelasticity, E is a function of Q to be defined. Next week when we start on aerodynamics. So what I am promising to you is that our generalized force in the right-hand side are coming from the aerodynamic force, and in the elastic framework, this force has to be expressed as a function of the deformation of the body. So this force will be expressed as a function of Q in Q coordinate. Or if you write your problem in bar coordinate, new coordinate, then you will express the generalized bar force in the as a function of the bar Q coordinate. It's the same. Okay. To be done in aeroelasticity. Next week. Now, at the moment, I'm supposing that this term is really a forcing term. Really a forcing term means I am assuming that this term is not depending on the state of the state variable of the problem. I am applying a force, and this force is independent by the consequence of this force, the displacement. Okay. Solution. I am trying to find a solution of this problem with initial condition. For Q, I know the displacement in a specific point, and I know the velocity Q dot at the beginning in specific point like this. So I want to solve this. I want to solve this. Solve for E identical equal to 0 for the unloaded case or free response case. Okay, but okay, excuse me, I have to add paper in my presentation. Just a few seconds. Just to have a break together. And okay, so free response problem. So I have this change of course, and I have just learned the lesson about the equivalence of this change of coordinate to the change of shape function. Okay, but practically now I want to write the following. I want to write m on q dot dot means m by zeta q bar dot dot plus k on q, which means k by zeta q bar. I should have E in the forcing problem, and then I want to pre-multiply this equation by zeta transpose, zeta transpose, zeta transpose. Why? Because I won't take the advantage of this. I won't take advantage but this. These two are the go now. Wow. And this allows to me to decouple my problem, my ordinary differential problem. This is mathematics. And so this means that here I have the famous constant in diagonal mn applied to q bar dot dot vector. This is a diagonal matrix plus another diagonal matrix with the famous k and applied to q bar, and I finish this part here, and eventually I have this quantity which I define like E bar. This is the generalized force, but for the equivalence I have just present to you, this generalized force, what is this? This generalized force has to be the projection of the physical force on psi bar. Okay, now I am a leader of this concept. I understand. Look, on this left-hand side, I have transformed the problem by using this concept. But this concept is equivalent to the concept to change the shape function. And then, necessarily, this new generalized force, P bar n, is the projection of the physical force directly on psi bar. Because the psi bar is the twin of Q bar. Okay, it's the same. Okay, in yes. But now I want to study the free problem. Free problem. Without this, free. No load, only initial condition. So I have this, and I have initial condition. Yes, I have initial condition on Q, but now I have to apply this initial condition on Q bar. I have to impose this initial condition on Q bar at the beginning and Q bar dot at the beginning. And remember that this relationship is valid in any time. So this relationship is valid also for the initial condition. So you may write this, but you may write also Q0 equal to zeta on Q bar 0. Okay? Okay. Diagonal, and therefore this problem becomes the following: M n Q bar dot n plus Kn Q bar n equal to 0. This is positive. This is positive. You can divide this by m n, and then you can write Q bar n plus omega square n Q bar n equal to 0. This is the ratio between Kn on Mn. And this is the famous positive eigenvalues. So you necessarily have in your life, for this kind of discretization, elementary oscillators representing the vibration of your generic structure as undergone to linear structure as undergone to a load. In this case, as undergone to the initial condition. So we have to solve this elementary problem. We know the solution for a pendulum, elementary linear oscillator like this, and we have that the solution is Q bar n is equal to, we have two constants to be fixed for this free oscillator, and we have an A constant, A by the cosine of omega nt, another constant by the sine of omega nt. And if you consider the value of this function at the beginning, and if you consider also the derivative of this solution, which is minus omega n an sine omega nt plus b n omega n cosine omega nt, you easily convince yourself that B and AM are related to the value of Q bar at the beginning and the value of Q bar dot at the beginning. In particular, you have the following. You have that Q bar n t is equal to Q0 n cosine omega nt. So an is Q0 at the beginning. And you have here plus Q dot 0 divided by omega n by sine omega 0 t, omega nt, excuse me. Okay, so this is the solution. I have the solution, but in the strange coordinate, in the coordinate of the diagonalized problem. Okay, I have the solution. This now I can go back and rebuild my original solution. And in particular, this is true for n equal to 1, 2, 3. So I can compact these several equations in a unique equation, vectorial equation like Q bar vector as equal to, I can introduce a cosine matrix diagonal. I am repeating this concept for many of you, but I want to be sure that everybody, my old student, other student, know this basic concept. Cosine matrix applied to the vector of the initial condition in the bar coordinate, plus here we have this 1 omega n, so I can introduce a matrix like 1 on omega n matrix like this, and I can introduce also an equivalent sine diagonal matrix like sine omega nt. This way for representing solution may result as redundant, but this is very effective for understanding this general procedure. And finally, these matrices are applied to the vector of the initial condition on the velocity Q0 dot. So we can call this elementary matrix this here like cosine matrix, like capital C function of t, and this is capital S function of t, and therefore this is our solution. But finally now we can go back to the original variable, and the original variable are the following. We have the Q original value, the solution of my problem, is equal to zeta on the new variable Q bar function of t, and therefore we have zeta as applied to cosine matrix applied to Q bar 0, but Q bar 0 is zeta to the power -1 applied to the original initial condition of my problem, which are this quantity here, Q0, plus we can introduce this omega matrix, which is a diagonal matrix to the -1, which is this matrix here. Next, we can introduce the sine. We have introduced the sine matrix as a function of t, also the cosine is a function of t, and then at the end we have zeta to the -1, the initial condition on the velocity, like here, dot 0. And this is the solution of, I finished, this is the solution of the free problem. Now, what we have done? We have an ordinary differential equation to be solved with the initial condition. We take this equation, we put it aside, and we have developed an algebraic eigenvalues problem. based on M and K, and we have found the eigenvalues of the eigenvector. Because of the properties of M and K, we have found that these eigenvalues are always positive, and we call them like omega squared. And we have also discovered that the eigenvector are real and orthogonal with respect to the mass matrix and the stiffness matrix. We take this opportunity to change the coordinate. We have a comment about this change of coordinate. In the reality, this change of coordinate from Q to Q bar is corresponding to a change of shape function by psi bar, that's by psi to psi bar. Okay, this is just a comment. But because of this change of coordinate, we are able to diagonalize our coupled ordinary differential equation into an uncoupled problem, and the uncoupled problem is solved as free problem. We solve, we go back to the original coordinate, and that's it. Finished. And this story means that the eigenvalues problem associated is the tool for solving the ordinary differential equation, because it's the tool for uncoupling the equation. That's it. Not physics or mathematics. But now I want to recover a physical issue with you. And this physical issue is on this kind of solution. Okay? In this kind of solution, I'm currently solving this problem. I have an elastic body like this. I can put an initial problem like this, release, and this is the solution. Okay? So this is a problem depending on initial condition. Q 0, Q dot 0. The field of velocity and the field of the displacement in the finite element degree of freedoms, because this is the meaning of Q and Q dot. Now I could answer to myself, are the found eigenvector a concept similar to the mode of vibration or not? In order to check this, I have to consider the mode of vibration as initial condition, because the definition of mode of vibration, namely the definition of steady wave in elastic solid, steady waves in elastic solid are wave not moving. If you impress this wave as initial condition and release in your body, in your elastic body, this wave keeps to oscillate without propagating to the solid. This is the concept of steady waves, or steady wave is a concept for physics, for Francesco Trequattrini. For engineering, we have mode of vibration. How can I check this? Easy. Try to put as initial condition one of the eigenvector. For example, the eigenvector number 4. What happens? And the velocity 0. Okay? What happens? I can cancel this part, and here I have zeta 4 instead of Q0. And when I apply this inverse to zeta 4, when I apply zeta minus 1 to zeta 4, I should have the following: 0, 0, 0, 1, 0, 0, 0. Because if I had zeta minus 1 on zeta, I should have identity. But if you take just the fourth column of this matrix, not all the zeta matrix, the fourth column, which is zeta 4, you should obtain the fourth column of the identity matrix. And this is the fourth column of the identity matrix. Okay, so you can cancel this. Instead of this, you can write 0, 0, 0, 1, 0, 0. Apply the cosine matrix by this elementary vector, and you should obtain here, let me write the solution in this page here. You should have zeta by 0, 0, 0 cosine omega 4 t, 0, 0, 0. Look, just here, this cosine diagonal matrix, in the fourth entry in the diagonal, you have cosine omega 4 t. Okay, so when you apply this on this, you have this. Oops, excuse me. You have exactly this here. And if you develop this final multiplication of this matrix, remember this is zeta 1 column, zeta 2 column, zeta 3 column, blah blah blah. By this vector you have the column 4, which is zeta 4, by cosine omega 4 t. And this is the solution. The final learning of this story is the following. If you impose the eigenvector, an eigenvector as initial solution, your final solution is the imposed eigenvector by an harmonic function like the cosine with a frequency equal to omega 4. But this is exactly the concept of mode of vibration. If you impose as a shape, as initial shape of a structure, one mode of vibration, in that case, and only in that case, so this is a definition of the mode of vibration, your solution will develop like that shape multiplied by an harmonic function. That means that each point of your structure is oscillating with the same time law, and actually an harmonic time law, and therefore any point reach zero maximum value and minimum value in the same time. So this is a mode of vibration. At the end of this story, the conclusion is that initially you evaluate an algebraic problem, but after this experience, you realize that the algebraic quantity like zeta 4 in the discretized vision of the Lagrangian quantity is multiple quotes, is the mode of vibration. And the corresponding omega, which are the square root of lambda, are the frequency, the natural frequency associated to that mode. Okay, so from now on, many people call this eigenvector and this eigenvalue, identify this eigenvector, this quantity and this other quantity, identify this quantity to the physical concept of frequency and mode, but they are not strictly. They are the mathematical vision, fruit of a discretization of that physical concept. Okay? Just to finish our fast review of structural dynamics, now I want to talk with you about the forced problem. But remember, the forced problem is not a problem. This kind of forced problem for the structure is not properly the problem of the aeroelasticity, because we are interested not on imposing E as a load imposed by God on the structure without being influenced by it. No, we want to develop the term like given by the motion itself in the elastic division. So what I am going to say to you from now on about the forced problem is not a total elasticity, it's standard structural dynamics. Okay, it's just a fast review about this. Okay, please, thank you. So, forced problem. For the forced problem, we have, okay, forced problem. We have this. This, which is, excuse me, 0, 0, through this transformation is equal to m q dot dot plus bar plus k q bar equal to e bar imposed. Not given by the motion. Plus initial condition on q bar. Q bar at the beginning, q bar dot at the beginning is equal to this known vector. Okay, but here we have a diagonal problem. The diagonal problem is the following. The diagonal problem is m n q dot plus q bar qn kn plus equal to e bar n. Now I want to propose to you a method for finding the final forced problem. The method is the method of Laplace transform method. So I want to take the Laplace transform of this ordinary differential equation, find the solution in terms of the Laplace transform, and then go back to the time domain. Okay, which is a fast way for integrating forced problems, very fast. So if you consider the Laplace domain of such a second derivative here, first of all, it is convenient to divide everything by n, and so we have 1 here, and here we have omega n, but do not forget this mass at the denominator here, please, in the forcing term. And take the Laplace transform of this, and taking the Laplace transform, we have s square, the Laplace transform of q bar tilde, we are using, yes, n quantity. I'm sorry for this double, but bar means new coordinate and tilde means Laplace transform. And do not forget two terms related to the initial condition. So we have s related to the initial value of the displacement. So this is a function of s. This is not. This is a constant. The constant of the initial condition. So this is also indicated like 0, 0. And another initial condition term related to q bar dot 0 m, another constant. And here we have plus omega square q tilde bar function of S again. And this is equal to the Laplace transform of E bar n divided by the mass. So I have just Laplace transformed this quantity in Laplace domain, and this is the result. This is the Laplace transform of q dot dot second derivative. So this Laplace transform of the second derivative will give this term, but also this term given by the initial condition, and the other. Okay, now I can algebraically find the solution, and the solution is this quantity here and this quantity here. So I can collect these two quantities in a unique quantity like q bar tilde n s multiplying s square plus omega square. Oh, excuse me, this is n. This is the ratio k on n, kn by mn, plus omega square n, and all the other term on the right hand side, we have q bar dot 0 n plus s q bar 0 n, and finally plus e bar tilde n divided by mn. We can easily move this term at the denominator, and we have the final solution like this, as equal to q dot 0 n divided by s square plus omega square n plus s on s square plus omega square n q bar 0 n plus e. Do not forget, this is a function of s. This is a function of s. So this function of s divided by mn and s square plus omega square n. So we have take a division by s square plus omega n to the power 2, and this formal division is in fact, the division is the opposite operation of the multiplication, and in Laplace domain the product and the division is something related to differential and integral. So we have integrated practically the equation. By dividing by this, we have find the solution. So in the time domain vision, we have integrated differential equation. In fact, if we go back to the time domain, we have the following. We have that q n as a function of t. Remember that this is a constant. Okay? And so we have to inverse Laplace transform 1 on s square plus omega square n, and this is equal to the sine of omega nt divided by omega n. This is the inverse Laplace transform of 1 on s square plus omega square n, and we have as constant this, the initial condition. Again, the Laplace transform of this is the cosine. And so we have the initial value of this by the cosine. And finally, we have to inverse Laplace transform this, but unfortunately, this is not an elementary inverse Laplace transform, but we have a product. We have a product of this function by this function. And the inverse Laplace transform of a product of function is the time convolution integral. So we can write this part of the solution as convolution integral. The convolution integral is apart of the constant Mn, is the convolution integral from 0 to the present time t, and here we have, this is the sine of omega n convoluted by with the variable tau, t minus tau, divided by omega n. And this is the inverse Laplace transform of this in the convolution form, and here we have this part to be convoluted with e bar n as a function of tau n in d tau. And this is the solution. As very, very final part of our consideration, we have to go back. We have to go back in the original variable, and we have finished. This is the solution of the force problem. I want to take this last very final maneuver of this demonstration next time, to have the opportunity to have a recap of everything we have done in this part, and then next time we will close this part and we will open the part related to the uncompressible unsteady flow. And the scope of the uncompressible unsteady flow is to give a solve to this function, forcing function, not as forcing function, but as generalized force as depending on the state space variable for a steady uncompressible flow in the first part and compressible flow in the second part. Of course, we are in the linear world, and so we have to linearize the flow, compressible and uncompressible. So very easy flow, but the only difficulty for this flow will be the treatment of the wake effect, because we will introduce delay mechanism in the aerodynamics, which are the key mechanisms for understanding the arising of the potential instability of the system, which is able to take a lot of energy by the airflow incoming. The airflow incoming is a source of energy and then a potential source of instability. Okay? Thank you. And I'm sorry for this long lecture, but we have closed before. I hope the hour are the first 2 hours, so you are very fresh in your brain. Please do not report this on your office. Thank you. I'm sorry. Write everything. Don't care about me about this. Thank you. Thank you.